Hello everyone. Good morning. I hope I am audible and visible to all of you. Everyone can see me? Oops, let me put it here. Okay. I'm audible, visible to all of you? Yes or no? I can hear wave of hands and welcome to this class. In today's class, what were we discussing in the last class? I think we were dealing with conservative and non-conservative forces, and we had done some pretty good problems on that.
Yes, sir.
Much more than enough. I hope you remember them, how to find out whether a force is conservative or not, and so on. Right? It was you discussed quite a few. I don't think we need to go any further. The name of the chapter, as you can see, is work, power, energy. Power is going to come at the last of this chapter. So the next thing that comes here is energy. So that is the heading for today. Energy. Energy. What do we understand by the term energy? Any idea? Anyone could tell me? Sir, this is energy. Sir, this is energy. What is energy? Most of you would know about it. What is energy? What is energy? The high school definition, 9-10 definition of energy is good enough. That is okay. Do you know that? Tell me. Energy, anyone? No one knows what is energy? Yes, beta? Can you just raise the voice a bit?
Capacity of doing work.
Yes, that is a very correct definition. And most of the definitions I have probably changed a bit. I've changed the definition of velocity that you might have heard, acceleration also I have changed it, but energy, maybe work done also I have changed because I have put in the dot product. But energy is the same definition as what we have been learning till now. Energy is the capacity, I hope everyone is writing, capacity or ability to do work. If you have energy, that means you are able to do work. And by work, what I mean, in physics, we are talking about energy in physics. In daily life, my kids has a loss of energy. He keeps on moving up and down, doing this and that. That is also energy. But here, the energy that we are talking about is the capacity of any body to do work. If it can do work, it has energy. Now, sometimes energy and work are used in the same sense, but remember, they are not the same thing. Uh, they are not the same thing, though they have the same unit. Let us first talk about the units. What type of quantity is energy? Scalar, vector? You must be knowing that this is a scalar quantity. And if we talk about the units, the SI unit is also joules or Newton meter. Now, in most of the cases, and I remember someone asking me about this, in most of the cases, we think of energy as same as work. Yeah, it is pretty similar to work. It is the ability to do work. You can also treat it as work, but they are different terms. So they have their different significance. And if someone has energy, it can definitely do work. But let us not confuse work with energy. Let us not say someone is doing work. Let us not say that he has got energy. He has definitely got energy, but that energy can be in different forms. So let us keep the two words. They are exactly similar. They mean similar, but let us keep them separately. Capacity to do work. Energy is not work. If you are doing work, you are not doing energy. You are spending energy. You have the capacity to do work, that is energy. Now this energy, you might have heard different forms of energy: electrical energy, solar energy, wind energy, wave energy, this energy, that energy. Well, they are all a part of physics, and probably you would have read about those things, how to convert from one form to another. What is fan? Fan converts electrical energy into mechanical energy. Motor converts electrical energy into mechanical energy. Let us not talk about all those things because that is not what we are concerned about. The topic here is mechanics. And in mechanics, what energy we are concentrating are basically two types of energies, which we'll be concentrating more on right now in this class, in this chapter. Can you tell me what are the two types of energy that we are going to learn about in this chapter? There, there are almost infinite types of energy, but we are not going to talk about those all types of energy. Nuclear energy, we're not going to talk about it here. It will be done in standard 12. What type of energy? Heat energy. Heat is also an energy. We've already covered that. Different branch of physics, thermodynamics. Right now we are in mechanics. What type of energy are we going to deal with here? Anyone, any idea? Obviously, you have an
Kinetic
idea.
energy and potential energy.
Yes, beta. We are going to deal with these two particular types of energy, which is one is kinetic, the other is potential. And in physics is pretty damn simple. Whatever is the name of that thing, we mean the same thing. So kinetic energy has got something to do with motion. Potential energy, you have the potential. You might have heard sir saying many times, you have got a lot of potential, you can do this. So potential simply means that you have the ability to do work or to ability to achieve something. You have potential, right? So two types of energy, potential and kinetic. If I add these two, what do I get? Potential energy plus kinetic energy. You might not know it. If I add these two, it is known as mechanical energy, total mechanical energy, ME. So ME stands for mechanical energy, KE stands for kinetic, and PE stands for potential. Now we are going to deal with all of these, but first and foremost, we are going to deal with the simplest possible one. Well, it looks simple, but it's very difficult to derive the amount of kinetic energy in a body. Einstein derived it, and I have the derivation. It is there in S.C. Verma if you want to see it. The last chapters, the theory of relativity. There they have derived how a body has kinetic energy. We are not going to get into quantum physics or relativity, so I am not going to derive how kinetic energy of a body is derived. The book may have a very simple derivation, but that is not the correct derivation, so I am not going to tell you that. Kinetic energies, that is the next heading, kinetic energy. Write the heading kinetic energy, and I would be waiting for someone to tell me what do you mean by kinetic energy. Kinetic energy, everything comes in the term kinetic. This is the term that we must be thinking about. Kinetic energy. What do you understand by kinetic energy? Anyone? And whatever you have learned in 9th standard is still valid. Nothing has changed here because you would have read it correctly. What is kinetic energy?
Motion is called kinetic energy.
Yes, beta?
The
Yes.
energy possessed by a body by its virtue of its motion is called kinetic energy.
Correct. Very nice. Kinetic, the term static kinetic, remember? Static kinetic. Kinetic means motion, something is moving. So kinetic means something is in motion, something is moving. So you can also call kinetic energy as motion energy. By motion energy, what I mean? If something is moving, the energy possessed by a body by virtue of its motion is known as kinetic energy. I hope you can write the definition. It is the energy possessed by a body, energy possessed by virtue of motion. If a body is moving, the energy it possesses and that energy can be used to do some work. That energy is known as kinetic or motion energy. Since it is a form of energy, it is a scalar. It has the same unit. Wherever you hear the term energy, the unit is always joule. So don't worry about that. Whether it is heat energy. In heat, we also have one more term, calories. I hope you know the relation between calories and joule, because at some point in time, and it is very near future that we, near past that we thought of heat as not energy. We were thinking heat is not energy, but then Joule came and made us understand that we are all fools, and heat is also an energy. Energy possessed by virtue of motion of a body is known as kinetic energy. We all also know its formula.
Sir,
What is the formula of kinetic energy, which we are not going to derive because it has to be derived using relativity. Okay.
sir,
Yes, beta.
what is meant by virtue, sir?
Virtue means energy possessed by virtue. I mean, by virtue we mean some quality. No, virtue is basically quality. You have a blessing or a quality. Here, what virtue means is if a body is moving by its motion, whatever energy it has is known as kinetic energy. I've just used an English term, nothing else. Just a dictionary wala term. So if you don't want to use this term, energy possessed because of motion of a body, you can use because. Energy possessed due to the motion of a body, you can use that word. It's just an English word, doesn't make. I am used to using this word, that is why I use it. That is, it has got nothing to do with physics at all. This is pure English. This is pure English, nothing to do with physics. You may not use it, doesn't matter. The definition still remains same. Am I clear? Okay, now what is the what is the what? What is the formula or the equation of kinetic energy? We are not going to derive it because that's beyond our course purview. What is the value of kinetic energy of a body? If a body of mass m is moving, how much will be the kinetic energy? Tell me. You must be knowing it. Tell me that now. No one knows it? No, no, no. It cannot happen. No one knows the value of kinetic energy in the class? Girls on the left, right, center. Boys on the right. No, boys are on the left. Girls are on the right. Okay. I get this problem with lefts and rights. No one knows what is its kinetic energy. No, 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 no. This cannot happen.
Half mv squares.
Okay, it is equal to half mv squared. Correct. Now, if I ask you, half is half, obviously it's a number. What do you mean by m? What is m here? What is m here?
Mass of the body.
M is definitely the mass of the body. Great. What about this gentleman V? What is this V? Or V squared? What is this V?
Speed.
V is speed. Oh, wow. V is speed. Why not velocity? What's wrong with velocity? Okay. I'm going to write speed oblique velocity, and I would prefer if you call it speed. I would prefer if you call it speed rather than velocity. Now, I don't have a problem with velocity, obviously, but remember there are two things that you must remember when you talk about velocity in case of kinetic energy. Now, kinetic energy in itself is a scalar quantity. Kinetic energy in itself is a scalar quantity. Velocity in itself is a vector quantity. Now, I am trying to explain a scalar in terms of a vector, that is like equating tomatoes with apple. I cannot equate a tomato with an apple just because they are of the same color. Okay, they are same color, red. That's why they are equal. No, they are not equal. Kinetic energy in itself is a scalar. But velocity, on the other hand, that you have written is a vector. How can I equate a scalar to a vector? It cannot be v squared. If I want to write it, it should be like this then. It should be equal to like this, half m v vector dot v vector. I don't know whether you have seen this anywhere, but this is how it should be written if I want to write it in the form of vector. Now I can write kinetic energy as half mv dot v. Now it is correct. Now I can call v as velocity. I'm very particular about definition. I'm very particular about telling you the right thing. Okay, now that is one problem that I told you, that if I have to write half mv square, let's not call v as velocity because it's a vector and the other side we have a scalar. So half mv dot v, then you can call v as vector. The second thing that I want to tell you, that it's better to call it as speed. Why it is better to call it as speed? First of all, it's a scalar. Speed is also a scalar. Scalar can be related to a scalar. Good. But the real reason is not scalar and scalar. The real reason is like this. And I'll try to illustrate it. I take time in explaining things, but you know, I understand that if you understand it correctly in the first case, my process becomes simpler. I'll just take the example of this gentleman. Something is moving in a circle. I think circular motion is already done. Yes or no? I think you are starting with rotation, right? So circular is already done. Done or not? Yes, good. Now, let us take that this is a uniform circular motion. I call it UCM. So the body is moving in UCM. If I look at here, velocity is v at point A upwards. At point B, velocity is like this. At point C, velocity is like this. At point D, velocity is like this. Now, if I ask you the very simple basic question, looking at the velocities at A, B, C, and D, are the velocities same? What is your answer? A, B, C, and D, are velocities same or different? A,
Same in magnitude.
same in,
Magnitude.
but,
Different in direction.
so will you call them same or will you call them different?
Different.
Well, it is different. Don't call them same at all. Yeah, the magnitude is same. What about kinetic energy? A, B, C, and D. What about kinetic energy? A, B, C, and D. Same or different?
Same.
What about velocity as A, B, C, and D? Same or different?
Velocity is different.
Oh, that is the thing that you must remember. Velocity can be different because of different directions. But at all points A, B, C, and D, speed is same, which is the magnitude of velocity. At point A, B, C, and D, speeds are same, but velocities are different. Kinetic energy is also a scalar. It is just a number. It has got nothing to do with direction. So let us not confuse velocity and kinetic energy. Let us not relate kinetic energy to velocity. Let us call it as half mv square, where v is speed, so that I always remember that if I have to change the kinetic energy of a body, I repeat, if I have to change the kinetic energy of a body, I must change its speed. I must change its speed, not direction. By changing direction, I am changing velocity, yes, but I am not changing kinetic energy, because kinetic energy depends on speed, which is the magnitude of velocity. Am I clear with this point? Why it is better to call kinetic energy as half mv square, where v is speed, rather than half mv square or v dot v, where v is velocity. Am I clear? Can I have some reason that you understand this? So this is one thing that you must remember about kinetic energy. Kinetic energy, if I write important points, point number one, kinetic energy depends on speed of the particle and it does not depend on velocity, because velocity can change by changing the direction, but kinetic energy will not change, it remains same. So if you remember this, I think this is good enough for you to understand what is kinetic energy. What is the next thing that you must understand here in this chapter? Kinetic energy is a very simple concept. There is not even a single question that I can make on this. What will I make? I'll give you a body of mass m moving with a speed v, and I'll ask you what is the kinetic energy. Anyone will tell me half mv square, sir. What comes next is the most important thing that you will learn, and that will, I mean, entire physics is important, but this thing will be with us for a very, very long time, and we must remember it. So we write the next heading, and the next heading is this: work kinetic energy theorem. Work kinetic energy theorem. It looks just too big, so I just call it work energy theorem. I just take off this K and I call it WET. So whenever I write WET, that means work kinetic energy theorem, or simply work energy theorem. I will not write this. I always try to save space. It saves energy, and it saves a lot of time. And time is what? That is going to matter in your final exam. If you can do it quickly, JEE Mains is all about speed. It has got nothing to do with knowledge. JEE Advanced, even more than 70% of the paper is about your speed. Only 20 to 25% is about your knowledge. Work kinetic energy theorem, WET, work energy theorem. What does it state? Anyone has any idea about this? You must have read this in class 9, because there was a point in time where I never taught 9th and 10th. So I had no idea what 9 and 10 kids do. But then I started teaching 3-4 years back. So I know what was the syllabus of CBSE in class 9, 10th. And I know that this is a part of it. So you must be knowing it. Tell me, what is work energy theorem? Anyone? Anyone knows it? If anyone knows it, please raise your hand. So if I'll see that anyone knows it, then only I'll wait. I'll move on. Yes, I see a raise hand. No, I don't see a raise hand. No one knows this? Work energy theorem, no one knows? Okay, okay, not a problem. Now, work energy theorem. So obviously the first term here is work. Someone has to do work, and somehow it has to be related with kinetic energy. Now, whenever you have work, you will have some force which is going to do that work. So what does work energy theorem state? It is a very simple theorem that says delta W, and I've told you why I write delta, because it's always between 2 points. Work done by all forces, delta W by all forces is equal to delta KE. Delta means change in kinetic energy, and this simple statement is known as the work energy theorem, which is going to be with us for a very, 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 very long time. What is state? If you apply force on a body, right now I'm talking about one body, we can always apply it on 2 bodies, 3 bodies, 4 bodies. I'll give you a question and you will be able to understand. Work done by all forces acting on a body. For example, if I just draw the simplest possible diagram, this is a flat surface, ground maybe. I have a body of mass m. I take the simplest possible example that I'm applying a force which is horizontal to the ground. Now this force is obviously going to move it. Let us not, this force is obviously going to move it. Let us say it has moved it. The point of application of force, I hope you remember all those things. Point of application of force, it has moved by a length del r, or the displacement is del r. You can also take that this is rough, so friction also comes into the picture. If it is rough, frictional force will be there. It will be kinetic in nature. Let me call it as Fk, kinetic. Fk, kinetic. Now, okay, if I draw more forces on this body, there is a gravitational force mg like this, and there is a normal reaction n. Now since the force is acting, the body may be accelerating. If the body may be accelerating, then at initial point the velocity may be u like this, and at the final point the velocity may be v. So far so good, we all understand this. Can I have some reason that we understand this? Some forces, all the forces that are acting on this body I have drawn. I have told you that initial velocity is u, final velocity is v. Now what has changed? Its velocity has changed, its speed has changed, the magnitude of velocity has changed, direction may not have changed. I'm not concerned about the direction because energy has got nothing to do with direction. The speed has changed. So what does this work energy theorem state? Work done by all forces. In this case, the forces are, I see there are four forces. First is normal reaction. The second one is mg, weight. The third one is kinetic friction. The fourth one is the applied force F. And this work energy theorem states that whatever work this all the forces together have done, it is just equal to the change in kinetic energy. It is just equal to the change in kinetic energy. Am I clear with this? Whatever work all these forces together combined work has been done, that must be equal to change in kinetic energy. Now let us, as an example or as a question, deal with this, and let us find out how will we apply work energy theorem on this particular problem. This is a problem, this is an example. Let me call this point as A and this point as B. So basically I'm applying work energy theorem. So basically I'm applying work energy theorem from point A to point B. So far so good? So I'm applying WET, work energy theorem, and it's better to write it like this in the beginning so that you remember, from A to B. A is the initial point, B, as you can see, is the final one. First of all, I write the statement, work done by all is equal to delta KE, change in kinetic energy. Change is always final minus initial, remember that. So far so good. Let us now talk about the various forces which are acting here. So work done by normal reaction, I call it as N, plus work done by the weight, which is mg, let me write it as mg, plus work done by kinetic friction, let me write it as small f, plus work done by capital F, that must be equal to your change in kinetic energy. Change in kinetic energy means final kinetic energy minus initial kinetic energy. So I write it like this, KEF minus KEI. F standing for final, I standing for initial. So far so good. Do we understand this? Can I have some reason that we understand this? Okay. Now let us deal with work done by all of these forces. Let us talk about work done by normal reaction. Who will tell me what is the work done by normal reaction? Who will tell me what is the work done by normal reaction? I'm waiting for your responses. Who will tell me that? It's a simple question. We have done it so many times. Work is already over. How much is the work done by normal reaction? Yes, I have someone. Tell me.
0, sir.
Well done, 0. I hope everyone understands this. Work done by wrong color. Work done by normal reaction is 0. Why it is 0? Normal reaction is upwards. Displacement is like this. Tongue, angle is 90. So this becomes 0. So far, so good. Let us now proceed to the next one. The yellow one, which is my weight. What is the work done by weight? Fatafat. Get me the answer.
0.
0. No questions asked, no answers given. Weight is downwards. Displacement is like this. Tongue. 0. Angle is 90. Let us come to the third one. Work done by friction. Now who will tell me this? Let us not worry about frictional force. How much is the value of frictional force? The value of frictional force is Fk. I've given you Fk. It is equal to mu mg and all that. Let us forget about this. What is the work done by frictional force? You can call frictional force as F. What is the work done by frictional force? Is it positive? Is it negative? No one knows what is the water by frictional force? Think.
minus FK.
Minus Fk. Yes, yes, minus Fk. Minus Fk into delta R. Yes or no? And here we are only talking about their magnitudes. Minus indicates that it is negative. Why it is negative?
Opposite to applied force.
Yes. Force is like this, but displacement is like this. Both are in opposite direction. So far, so good. Shall I move again? Okay, the last one, but not the least one. Oops, this is too dark a color. I must change it. This one will do better. What about this, gentlemen? What is the work done by the applied force F?
F delta R.
Positive or negative, bacha?
Positive.
Yes, F into delta R. That must be equal to KEF minus KEI. Tell me what is KEF?
Half mu square.
Final, bacha, final. Look at the final.
Half
I'll mark
mu
it. You look at this. KEF. Yellow. Just tell me. No. मैंने गलत कर दिया. KEF. Which one is KEF and which one is KEE?
half mv squares.
So it must be equal to half mv square minus half mu squared. Am I clear? Am I clear with this one? Do we understand this? So this is how you apply work energy theorem. Now at this point in time, I just remember something. So please let me know in the next class. That in the previous class, I think we were doing a question on conservative forces, non-conservative forces. And I'd given you one question for homework. We discussed it in the class next day. I think we have done a mistake in that question, and I will correct that mistake in the next class. So please remind me, sir. Please do that question again. Someone asked me, Anak probably asked me in the doubt on my thing, and then I realized that probably I have done it wrong. Unknowing mistake I have done in that question. So I will be doing that question again in the next class. Will you remind me, everyone? That question where force, there was some conservative force, so I don't have that. I will open that class, and then we will do it in the next class, because I think I have done a mistake there in that particular question. So remind me in the next class, because I just can't break the class here. I just remembered it because I just made a mistake here. I was painting yellow with U and yellow with KEF. Similar mistake I have done over there. That is what that clicked. So in the next class, what are you going to do? You just remind me, sir, we are supposed to do that question again. Okay, done? Chalo. Do we understand this work any theorem now? So far, so good? Chalo. If you have understood this now, you will have to solve a very simple question, and then the question will get progressively difficult. And the question that you're going to solve is the simplest possible question. We have done this question in the first chapter, yes, but again, now we are going to do it in this class. There is a block of mass m kept at a height h. Obviously, this block is at rest. So probably I'm holding it somewhere here. I'm holding it somewhere here. Oh, you can see it now? Probably I'm holding it somewhere here. I just missed it because I'm not seeing your screen. I'm seeing yourself. Okay, I'm holding it somewhere here. This is ground. This is ground. I'm holding it somewhere here. This side is h, and I drop it. So what happens? It falls. Obviously, it falls. Now, before it touches ground, it has some velocity. What is the velocity with which it touches ground? find velocity v. So if I just draw it here, that this has fallen over here, with what velocity it has fallen. Now remember, many times students ask me, sir, how will we find out? How will we find out? A question has to be done with this work energy theorem. So the biggest hint I can give you, and note it, if a question asks, if in a question you are asked to find out v, final velocity, or u, then 99.9% this question has to be done with work energy theorem. Remember that. 99%. It may be in this chapter, it may be in electrostatics, it may be in any other chapter. It may be even in your elasticity wala chapter. If it is asking for final velocity v, it has to be done with work energy theorem. Same work energy theorem, but the forces will be different. Secondly, if a question asks you acceleration, what is the acceleration of the body? Then 99.99% that question has to be done with Newton's laws of motion. You will have to draw free body diagram, find out the forces, do this, do that. That doesn't mean that in work energy theorem you do not have to draw free body diagram. You have to draw, but the free body diagram is not that important. A simple free body diagram will do your job. So these are the two things that you must remember. And the biggest hint given in this question is that you have to find out the final velocity v. Your time starts now. If you can do it, you can do it by what you know from standard 9th. You can do it from what you know from the first chapter, motion in one dimension, because this is simply motion under gravity. But right now we are trying to do it with the concept of work energy theorem. I'll give you a minute, think about it, give me the answer.
Sir,
Yes, beta?
sir, when we will discuss question paper, sir?
When we will discuss?
Question paper.
Oh, I did not get the question paper. Do you want me to discuss? I don't have the question paper, beta. You want me to discuss the question paper? We'll discuss it, not a problem.
Yes, sir.
If there's any question, you let me know which question you want to discuss. We'll discuss that. Okay?
Sir,
Yes, beta.
we got DPP also, sir.
Okay. DPP, are you solving the DPP now?
Yes, sir.
Okay. So what I'll do is, I'll take maybe tomorrow. I will discuss the DPPs, whatever doubts are there in DPPs, and we'll also discuss the question paper. Once you get I don't have the question paper, so I don't know. I'll get the question paper, discuss. Is there any particular question that you have not understood?
Yes, sir.
Okay, we'll discuss that. Don't worry.
Okay, sir.
Okay. So, how are you going to solve this question? Let me know. You have a minute to think about it. Okay, anyone with an answer? How to do it? What will you do? Answers are not important. Important is how you have attempted the question. Anyone? No one? Let me call this point A and let me call this point as B. So what I'm going to do is I'm going to apply work energy theorem from point A to point B. My A becomes the initial point. My B becomes my final point. So far, so good. Now, as soon as I write WET, I would write work done by all forces is equal to change in kinetic energy.
Sir,
Yes, beta?
answer is under root 2GH.
Wow, very good. Please help me out. How you have done this?
Applying work energy theorems.
Well done. So I have written the work energy theorem. Am I correct?
Yes.
Okay. Now tell me what are the forces acting here?
Mg.
Okay, there's only one force acting. I am not. We are neglecting here air resistance. So there's only one force which is acting here, which is mg. Yes. What next?
Work done is mgh
Plus or minus?
plus
Y plus? Y plus?
gravity
Because
is downward.
it is moving downward. So force is wrong color. Force is mg, and it is moving down h. So what is the work done by this force? The work done by this force will be equal to
Mgh.
plus. It's always better to call it plus mgh. Am I clear, everyone?
Yes.
Okay, plus mgh. That must be equal to change in kinetic energy. Change always means final. Final is b minus initial, which is a. So what is that? That must be equal to half m v square minus u. So far, so good. U is point A and it is at rest. Everyone can see everything is in yellow. A is the initial point. It is at rest. Kinetic energy is 0. B is the final point. Velocity is v. Kinetic energy is half mv square. Just put the values, get the answer, stay happy. I can just now put the value of work done. And I will get my answers here. So this is plus mgh is equal to half mv square. M say m will get cancelled. I will get v as root over 2gh, which is the same answer I would have got if I would have done it by the concept of motion in one dimension, motion under gravity. And here is a very good thing that I would tell you. Since you are in the engineering branch, I must be tell you, whenever we have written this equation, I hope everyone has understood this. So far, so good. Can I have some raise hand that we have understood this? Students on the left, girls on the right, center. Okay, now here is the small information that we would add now. As I tell you always, I always keep on telling you that I only tell you on a need to know basis. Need to know basis. I only tell you what you need to know at that point in time. But there will be a time where I'll tell you more about it. Now, today is the time I'll tell you more about it. I'm in a good mood, so I'll tell you more about it. Okay. Remember this equation? V square is equal to, important, V square is equal to U square plus 2A into delta R. Do you remember this equation? Everyone? Do we remember this equation, everyone? Yes or no? Okay. Now we'll try to look at this equation in a different way, and then you will realize, oh, it means this. Okay, what I do is, I multiply both sides by m. So far, so good. Nothing has changed. I've just multiplied it by m on both sides. Then I take mu square on this side. And I've written it like this. Then this 2 is taken in the denominator on the other side. So now the equation looks like this. Now look at here. I have mass multiplied by acceleration. The body is accelerating. I multiply it with the mass. I multiply this body with its mass. This acceleration with its mass. So basically, it gives me net force. Net force is mass multiplied by acceleration. Yes or no? So this is basically net force. Oops, wrong color. This is net force multiplied by delta R. Now look at this equation. Does it sound familiar now? Can you see it in a different way? What is this? What is this? Anyone?
Final kinetic energy.
Yes. This is KEF, final kinetic energy. What about this, gentlemen?
Initial kinetic energy.
Yes. This is KEI. What about this entire thing?
Work done by all forces.
Yes, work done by all forces. Shabash. Well done. Now you are on the right track. Work done by all forces. So you remember this work energy theorem, which we are doing right now. We had actually done it in the first class of the first day when we had done this equation. This is the equation of work energy theorem put in a different way. Not in a different way, it is put in the same way also, multiplied by mass divided by 2. Now, this is not the exact way it should have been written. Now, I'll tell you the exact way it should be written. This is the way that I've written it is this is a 9 standard way of writing it. This is not the way it is written as. So now look at the way that it should be written as. It should have been written like this. The first equation should have been written like this, and now probably it will make more sense to you. It should have been written like this. V dot V. Oops, why I'm writing U? V dot V is equal to U dot U. Now, if I have written this equation in this form in the first class, you would have said, "Sir has gone mad, and we don't understand anything. Let us pack our bags and look for some other." So that's why I did not write it on the first class. 2 times A dot delta R. This is the only way I should have written this equation, because the way I wrote it is absolutely wrong. But that is how books write it. Because V dot V is V square actually. U dot U is U square. But if I don't write the dot here, I miss the main point of that entire thing. Are you getting me? This is the right way of writing that equation. Do you understand this? Can I have some raise hand that we understand this? Correct. Now, this is one way of writing it. This is the exact correct way of writing it. This is how you can derive it. There is no other way of deriving it. The second way of writing it like this. Half M V dot V minus half M U dot U is equal to F integral of f net dot dr. If you write it like this, everyone will be like, oh, what you have written? But you have simply written what? You have simply written what? You simply written work kinetic energy theorem. Do you understand this? Yes or no? It has got too complicated for us to understand. Can I have some raise hand that you understand this? If you don't understand such simple, what should I take? Technical things, you can just write it like this. Third point, third form, work done by all forces is equal to change in kinetic energy. That's it. We have done the same thing in the first class when we did equations of motion. But as you can understand, I could not have written it in this form because it would not have made much sense to you. Right now, it will make sense. Please note it down. I hope you understand this F net dot dr is your work done by all forces. And the rest thing is your change in kinetic energy. I'll give you a minute to write it down. Okay. Since we have done this, we will wind up this class with a simple question. And the question is like this. I have an inclined plane, inclined at an angle of 37 degrees. I have a block of mass m kept at a height h. There is no friction. In the next question, we will bring in friction. The next question, we will bring in friction. Now, when it reaches the lowest point, it is obviously at rest at this point. When it reaches the lowest point, there is no friction. What is the velocity of this gentleman? You have a minute to think about it. Well, anyone would like to tell me? Let me call this point as A. Let me call this point as B. How are we going to do this? Let us first draw the free body diagram. The weight is mg. Downwards. Normal reaction is upwards. We are going to apply work energy theorem from point A to point B. So far, so good. We all understand this. We are going to write the work energy theorem. Work done by all forces is equal to change in kinetic energy. I have written this. What are the forces here? One is normal reaction. What is the work done by normal reaction? Anyone? What is the work done by normal reaction? Anyone? Normal reaction is like this, upwards. Displacement is like this. What is the work done by normal reaction? It is zero. Yes or no? Do we understand this? Work done by normal reaction is zero. Do we understand this? Can I have some raised hand that we understand this? Great, great, great. Then the next is gravity. Gravity force it downwards. It is moving downwards. What is the work done by gravity? Anyone tell me?
mgh
Plus or minus?
plus mgh.
Plus mgh. That is the total work done. I will just write it as plus mgh. That should be equal to initial kinetic energy minus final. As you can see, I am going to mark the initial point A. The kinetic energy there is zero. We know all that. We all know that kinetic energy is zero. So this is zero. No problems. No questions asked. No answers given. The final point happens to be point B. The kinetic energy here is, oops, I will put it here. The kinetic energy here is how much? Half mv squared. Half mv squared. The kinetic energy is here. Final minus initial. The pink one minus the yellow one. Pink one minus yellow one. And the answer is half mv squared minus 0. M same getting cancelled. I have the final answer as V is root over 2GH. And that is the final answer that I was looking for. Everyone got this? Yes or no? Online class, offline class? So this is today's class. Well done, everyone. I hope you have enjoyed it. The next class we'll be discussing your question paper, and if there's any question in the DPP, I'll have a look at it. We'll also discuss that, and also remind me of that question. So in the next class, we'll be dealing with questions and all. That's it from my side today. I hope you'll enjoy this class. If there's any doubt, I'm here. You can ask me. Else, it's a wrap from my end. Class is dismissed. I hope you have a nice day. Keep on studying harder. That is the only thing that you can do right now. Take care.